Momentum change and impulse. Suppose that there is an event that changes an object's momentum from p0, the initial momentum, just before the event, by delta p, which is our change in momentum, to p sub f, the final momentum, just right after the event. The equation for momentum change would be p0 plus delta p is p final. Here's our momentum change equation from the previous slide. Now Newton's first law tells us that the velocity, and so the momentum, of an object won't change unless the object is affected by an external force. Let's go ahead and define impulse, and the abbreviation for impulse is just capital I, as an external force acting on the object for a time delta t. The impulse changes the momentum of the object. So I is equal to delta p, which is pf minus p0. Putting these two expressions together results in the impulse momentum equation. Impulse, which is f delta t, equals a change in momentum, which is equal to the final momentum minus the initial. There is no specially named unit for impulse. We just use the product of the units of force, newtons, and time, seconds. So we get kilogram meters per second. This is the same unit that we use for momentum, which is a good thing. Let's look at the impulse momentum equation graphically. We have impulse is F delta t, force times the time that it's exerted over. Force is inversely proportional to delta t. So for example, if we change delta t by just a little amount, we can greatly change the force exerted on an object. For example, let's take this point over here. The time there is a little less than 1 second, and the force is about 130 newtons. If we just change to about 4 seconds, if we extend the duration of the impulse to 4 seconds, you can see how the force drops dramatically. And as you go longer and longer at your time interval, there's less of a change in force because frankly it's getting very tiny. Another way to look at that is we have impulse divided by delta t equals the force applied. So you can see as delta t gets smaller, F gets a lot bigger. Now we're just going to work with the magnitudes of the impulse and momentum going forward, so we're going to leave the vector sign out for now. The bold here is to show that if delta t is small, F is large. If delta t is large, F is small. The inverse relationship of force and time interval leads to many interesting everyday applications of the impulse momentum equation, such as car structural safety design, car airbags, landing on the ground after you parachute safely from an airplane, the martial arts, and both hitting and catching a baseball. We're going to look at two specific cases from the previous list, car airbags and hitting a baseball. The analysis we're going to use is very helpful. You can use it in many other cases in physics when you have an equation with 3 variables. In this case, the 3 variables are force, your time interval, and of course, impulse, which again is your change in momentum. So you have the 3 variables. You have to decide, depending on what case you're analyzing, which value is fixed and then which will be varied, and then that will determine the impact on the 3rd variable. For example, for the car airbags, we'll fix delta p. We'll take different scenarios of the time interval and see what the impact on the force is, and in this case it will be the force on the people inside the vehicle. For a bat hitting a ball, we will fix the force with which the player hits the ball, we'll vary the time interval, that's how long the ball stays in contact with the bat, and we'll see what that does to the momentum of the ball. In the dynamics unit of this course, it was shown how during an accident, seat belts protect passengers from the effect of Newton's first law, the law of inertia, by stopping the passenger with the car and preventing them from striking the dashboard and the window. Inertia, the law of inertia says you keep moving until there's a force that stops you. That's one of the things it says. So if you are not seat belted in, the car stops because it hits something or you apply the brakes very quickly. And if you are not seat belted in, the frictional force between your body and the seat is not enough to stop you. So you'll go flying forward as the car stops, which is never a good idea. Also, the seat belts provide another benefit explained by the impulse momentum equation. And this benefit is greatly enhanced by the presence of airbags. Can you see what this benefit is? Take a second before you go on to the next slide and see if you can figure it out. The time interval delta t. The seatbelt increases the time interval that it takes the passenger to slow down. You don't go flying forward and hit the glass. The seatbelt has a little play, so you move a little bit, but then it slows you down when it tightens up. The biggest effect here is the airbag. That increases that time interval. It rapidly expands, providing a cushion that you strike. Then it deflates, and it's slowly compared to how fast the car has stopped, bringing you to a stop. Very analogous to if you fall from a height of 3 feet onto the floor, that hurts. Your time interval of this stop is very, very short. If you fell the same height onto a mattress, the mattress would give, increasing the time of you stopping. There'd be a greater time interval. Earlier we stated that delta P for this example, for the car airbag would be fixed and delta T would be varied. Well, we just talked about why delta T is varied. Why is delta P fixed? Delta P is fixed because as long as the passenger remains in the car, which of course is another wonderful reason to wear your seatbelt, the car and the passengers started with a certain velocity and finished with a final velocity of 0, independent of the seats or the airbags. Whether you had them on or not, the car is going to stop. By rearranging the equation, F is delta P over delta T, where F represents the force delivered to the passenger due to the accident. We have the impulse momentum equation up here, where F delta T is equal to the change in momentum. And we did a little rearranging on the last page, and we had force is delta P over delta T. So delta P is fixed. So we just draw a little horizontal line there showing that it's fixed. Delta T, we've extended the time interval by using the seatbelt and the airbag. So delta T is going to increase. This is a handy little trick to see what happens to the various variables. If you increase the denominator, you decrease the entire number. So the force, and this is the force on the passenger, decreases markedly. That will mean less physical harm to the people inside the car. Another benefit from the airbag is pressure. Pressure is force per unit area. By increasing the area of the body that feels the force, remember the airbag is pretty big, less pressure is delivered to all parts of the body. That will reduce the chance of puncturing the body, which is also a very good thing. Example 1, impulse. A constant force of 12 newtons acts for 5 seconds on a 5 kilogram object. What is the magnitude of the impulse delivered to the system? What is the change in the object's momentum? And what is the change in the object's velocity? We list our givens, and then to find the impulse, we use the impulse momentum equation, which is force times time, change in time. Substitute our numbers in, and we get 60 newtons per second. That's the impulse. What is the change in the object's momentum? Well, the change in momentum is equal to the impulse, so that is also 60 newton seconds. And another way to write Newton seconds is kilogram meters per second squared times seconds. Seconds cancel out there, and you get kilogram meters per second. Now we need to find the object's velocity, and we'll do that by using the momentum equation. Change in momentum is equal to the mass times the change in velocity. We solve that for change in velocity by dividing both sides by m. We substitute in our 60 newtons per second that we got on the previous slide for the change in momentum, divide it by the mass, and we get change in velocity is 12 meters per second. A 0.050 kilogram tennis ball moves at a speed of minus 10 meters per second. That means it's moving to the left, as we show down here, and is struck by a racket, causing it to rebound in the opposite direction at a speed of 16 meters per second. What is the change in momentum of the ball? What is the impulse exerted on the ball? And what is the impulse exerted on the racket? What is the change in momentum of the ball? Well, our momentum equation is delta P is mvf minus mv0. So we substitute in our values and make sure you use the negative sign here for the tennis ball moving to the left, and we get a change in momentum of 1.3 kilogram meters per second. Now, an easier way to do that would have been to factor out the m, so you only have to multiply by it once. I mean, both ways are correct, but this is a little more elegant. What is the impulse exerted on the ball? Well, let's use our impulse momentum equation, and the subscripts here show this is the impulse that the racket delivers to the ball, and it's equal to the change in momentum of the ball, which is 1.3 kilogram meters per second. Then what is the impulse exerted on the racket? Here we have Newton's third law. The impulse that the ball exerts on the racket is negative the impulse of the racket that exerts on the ball. So we have a negative 1.3 kilogram meters per second. The force that the ball exerts on the racket, and of course you use force to calculate impulse, is part of an action-reaction pair with the force that the racket exerts on the ball. So the two impulses are equal in magnitude and opposite in direction. A 0.030 kilogram golf ball is hit off the tee at a speed of 34 meters per second. The golf club was in contact with the ball for 0.0030 seconds. What is the average force on the ball by the golf club? We list our givens, and we add that the initial velocity is 0 meters per second. That wasn't given, but the golf ball is just sitting there on the tee. So we start with the impulse momentum equation. We substitute in our values, and here's our initial velocity is 0, so that term does not contribute. And we get an impulse of 1.02 Newton seconds on the golf ball. We then go to our impulse definition, and since we want force, we have to isolate force in that equation, so we divide both sides by delta t. We get force is I over delta t, substitute in our numbers, and we get 340 newtons.